If we use scientific calculations to experience the journey of the movie Interstellar, what kind of experience would it be? Suppose you follow Cooper and the others aboard the Endurance ring-shaped mothership to the wormhole near Saturn. And this journey takes only 2 years. At this time, just using the orbital radii of Earth and Saturn, you can roughly calculate the shortest distance between them, which is also the travel distance of the Endurance, about 1.3 billion kilometers. Thus, it can be deduced that the speed of the spacecraft is about 70,000 kilometers per hour. But in reality, as the fastest manned spacecraft in history, Apollo 10 had a speed of 40,000 kilometers per hour. According to the current pace of technological development of mankind, reaching the speed of the spacecraft in the movie in the future is completely consistent with scientific settings. At the same time, the spacecraft was also designed as a rotating ring structure to generate artificial gravity through centrifugal effect. When we use the centrifugal acceleration formula, we can deduce that half a rotation of the spacecraft takes 5.7 seconds. A full rotation then takes 11.4 seconds. In order to generate the same gravitational acceleration as Earth's 9.8 meter s2, the spacecraft would need to have a radius of about 30 meters, which means a diameter of 60 meters to achieve this. As a comparison, in reality, the International Space Station is about 70 meters wide. Therefore, this setting is also completely consistent with scientific logic. After 2 years of flight, the spacecraft finally arrives at the wormhole near Saturn. As the most fascinating space-time tunnel in physics, a wormhole is a three-dimensional tubular structure that connects two distant regions of the universe together. It not only allows the spacecraft to travel through this three-dimensional space, but even light can move inside it. Therefore, from one end of the wormhole, it is possible to see the image of the other end. To explain the realism of the image, we attempt to simulate it by connecting two regions of the universe with a cylinder and smoothing it out to achieve a better transition effect. At the same time, place a camera on one side of the wormhole and place a starfield image on each side so the camera can simultaneously receive light from both sides. Then the light reaching the camera can be converted into corresponding pixels. Through ray tracing technology and the geodesic equations in general relativity to track the trajectory of light in distorted spacetime, when calculating the position of each pixel, as well as the color received by the camera at that pixel, and when it is animated, we obtain the wormhole image in the simulation program. At this moment, we are astonished to discover that it is extremely similar to the wormhole special effects in the movie. But the problem is, when we move along one side of the wormhole through the camera, we find it completely different from the special effects in the movie. Perhaps Nolan did this so that the audience could better understand the visual experience of the spacecraft crossing the wormhole's surface. If the wormhole structure is stretched, we will then see this fantastic scene inside the wormhole in the simulated image. After leaving the wormhole, the Endurance arrives near the supermassive black hole, Gargantua. Around the black hole, several planets orbit it, and the first target for us and Cooper and the others is the very special planet Miller. Its surface is completely covered by ocean, and its orbital path is very close to the black hole, which results in not only extreme tidal phenomena that can form waves as high as 1 kilometer, but also extreme time dilation effects. 1 hour on its surface equals 7 years on Earth. First of all, regarding the phenomenon of extreme tides, through the gravitational pull of the black hole and the centrifugal effect of the planet's orbit, we can calculate the net tidal force using Newtonian classical physics. It can be seen that this force squeezes water from the equator to the poles. In this process, the tidal force does work on the water, and the amount of work is equal to tidal force x displacement, where the displacement refers to the radius of the planet. Considering that the work is equal to the gravitational potential energy of the water, we can calculate how far Miller's planet is from the black hole to form kilometer-high waves. According to the movie's setting, the mass of the black hole Gargantua is 100 million times that of the Sun. It can be calculated that Miller's planet is about 45 billion kilometers away from the black hole, and the black hole's radius is about 300 million kilometers. When we compare this distance with the movie's scenes, we find that this angle is very close to the view of the black hole from Miller's planet. As for the issue of extreme time dilation, for a static black hole, when we substitute the distance into the time dilation formula, we obtain that the time dilation on Miller's planet is only 1.05 times, which is far from the setting in the movie. If we want to reach a time dilation of 60,000 times, the planet must orbit on the photon sphere of the black hole. And at this position, only photons can stably orbit the black hole. In other words, there cannot possibly be any planets in this region. But this calculation only applies to a static black hole. According to general relativity, a black hole is a rapidly rotating celestial body. The faster its rotation speed, the more stable the nearby orbits will be. Through calculation, we find that if we want to keep the time dilation factor at 60,000 times, then Miller's planet must be only 6,000 kilometers from the black hole's boundary. And the black hole's rotation speed would have to be just 1/trillionth slower than the speed of light. This is clearly an exaggerated visual effect. When we follow the endurance to the front of the black hole, we feel an incredibly shocking visual scene. So, what does a real black hole actually look like? To simulate the true image of a black hole, we also use ray tracing technology and the geodesic equations in general relativity, and finally obtained this black hole image. At this point, we find that a bending phenomenon occurs behind the disk. This is Einstein's gravitational lensing effect. Due to the strong gravity of the black hole, light rays are deflected, so that when we look in a certain direction, the objects we see are actually located elsewhere. Yet this phenomenon was not shown in the movie. At the same time, near the black hole, there is also an accretion disk. When we simulate it, we see that the black hole's immense gravity distorts the light emitted by the accretion disk itself. And the rotation speed of the accretion disk is extremely fast, almost approaching the speed of light. Under constant friction, its disk temperature can even reach hundreds of millions of degrees Celsius and produce intense and deadly radiation. When we filter through the entire electromagnetic spectrum, removing all light except visible light, we then see in the spectrum the disk appears as a higher energy blue color. This also explains why stars with higher temperatures emit a strange blue light. And such extreme physical phenomena would directly destroy the spacecraft. Therefore, Nolan not only weakened the temperature of the accretion disk in the movie and reduced the pressure inside it. At the same time, due to the rapid rotation of the accretion disk, the light on one side of the disk appears brighter than on the other side. This is the marvelous Doppler effect, and this phenomenon was also not presented in the movie. In order to escape the black hole's gravitational field, Cooper decides to lighten the endurance and goes alone into the event horizon of the black hole. At first, the scientific community generally believed that the singularity of a black hole was a point-like object. Later, through theoretical speculation, it was suggested that the singularity inside a black hole presents a chaotic, twisted structure. At the same time, researchers also found that when matter falls into a black hole with sufficient mass and a sufficiently fast rotation speed, under the effect of time dilation, the relative motion of matter inside the black hole appears to slow down and continuously accumulate, eventually forming a large-scale singularity. This singularity is not only relatively mild, but also produces relatively weak tidal forces, making it theoretically possible to survive. But in order to avoid being caught by another singularity, one must dive into the black hole at nearly the speed of light. And the gargantua black hole in the movie precisely borrowed this theory, allowing Cooper to successfully accelerate into the singularity and survive. Although no one knows what is actually inside a black hole to this day, the movie wanted to reflect the multidimensional spacetime structures mentioned in string theory and brain theory. as well as quantum gravity effects. Thus, Cooper enters a four-dimensional hypercube, in which each face is a three-dimensional cube, equivalent to each face in 3 dimensions being a two-dimensional plane. This allows Cooper to enter one face of the hypercube and ultimately arrive at his daughter's room. Although the two are separated by a vast distance, the hypercube is already within anti-de Sitter space, thereby greatly shortening the distance between them. At the same time, because we, in 3-dimensional space, cannot perceive the existence of 4-dimensional space, therefore light can only travel from 4 dimensions to 3 dimensions, but cannot travel from 3 dimensions to 4 dimensions. Thus, Cooper cannot directly communicate with his daughter. But at the same time, Cooper also accidentally discovered that gravity can pass through this barrier and convey information. This is because, in string theory, the basic unit of the universe is not a 0-dimensional point particle, but a 1-dimensional string. And the vibration modes of the string determine the properties of the particles. So in theory, gravity can penetrate all dimensions. Therefore, Cooper used gravity to transmit quantum data into 3 dimensions, providing the key information needed to solve the equations, which enabled his daughter Murphy to master the method of controlling gravity and reduce the gravity on Earth's surface, thus allowing the giant centrifugal space station to be launched into space, ultimately saving all of humanity.